Good afternoon, everyone. We're down to the last lecture of this semester. It's been an interesting one. Before I get into the actual material, a couple of comments. One, as many of you noted before, the last lecture's notes started at page 163. 162 is not missing. There is no 162. There's some issue with numbering that needs to be corrected in my master file. Okay, what else? Assignment 8 has been posted. The course link quiz is open for you to submit your responses, and I've put the course link submission deadline to Friday morning, 8 a.m., but of course you can get it in by Thursday if you wish, particularly if your family has something scheduled for the Good Friday. What else? Last day, I talked to you a little bit about the final exam option. Some of you have been emailing me with your option. I will not be looking back at those emails. What I will be doing is setting up a quiz on CourseLink. This quiz will essentially be one question about whether you intend to write the final exam or not. When that is posted, I will notify you and ask you to go in and actually submit your response to that. This also allows me to put a flag in my in the grade book as to which choice you want to choose. If you decide you want to change your mind as you get closer to the exam, then you should be able to go in and resubmit your response. One of the main issues for me is to just understand how many of you intend to be writing the final exam. This has implications for the grading and the TAs and so forth as well. Okay, what else? I will not be calculating pre-final final grades. Some of you have been asking me what your current grade is. You have all of your assessments that have been graded up till now. You have, and the test 1 and test 2, that is all that I have as well. The course weighting is also available, so you can work it out, but I will not be doing that multiple times. However, after test 3 and test 8 are graded, so that's when I've got all of the assessments on my end, I can go back and look at those as well. Okay, final exam. It is currently scheduled for Monday, April 27th with a start time of 1 p.m. I've been told that exams have been blocked for 4-hour windows to allow for those who are writing with SAS, as well as to allow for technical problems, but I will get back to you with more details about that as the date gets nearer. Okay, I think those are all of the comments I wanted to make before we get into the lecture. And now, what I wanted to do was actually start at page 163. So this was the first lecture note from last day. I just wanted to make a clarification, and this is more just for big picture understanding. So last day we'd started off by looking at the salt intake and cardiovascular disease example. And what we had seen was that when we looked at defining the X variable to be 1 when some subjects on the low salt intake relative, and looked at the odds ratio for the odds on the low salt intake relative to those on the high salt intake, what we found was that our odds ratio estimate was 0.824, which is less than 1. And so we had worded this as the odds of developing cardiovascular disease for the low salt group are reduced by a factor of 0.824 compared to the high salt group. So what does that mean? From another perspective, you could think of it that if the odds of developing cardiovascular disease for the low salt group is reduced by a factor of 0.824, that means that the odds are about 82.4% of that of the high group. So implicit in this means that the odds are reduced by 100 minus 82.4, which equals, 100 minus 83 would be 17%. And then we've also got the 0.4. So this would is equal to 17.6 percent. Okay, so it's reduced by a factor of 0.824. That means it's reduced by 17.6%. Okay, so you could take one reduced by 1 minus, this is getting messy, 1 minus 0.824 times 100%, which gives us 17.6%. Okay, so when you're going through and thinking about these, it's not that it's reduced by 82.4%, it's reduced by 17.6, which means it's a factor of 0.824. So I hope that helps in terms of interpreting odds ratios when you see them, say, in a research paper or something like that. Okay, so today, what I wanted to do was move on from where we left off last day. We worked through a couple of examples, one being the cardiovascular disease one that we just discussed, the other one being the movies example. And so we've more or less shown how you can set up a simple logistic regression, how you interpret the model parameters, how you can perform a test on the slope parameter, as well as confidence interval for the odds ratio. What we didn't do, so this is page 169, our new notes for today, is that we didn't go through what the assumptions were for logistic regression. Remember, in the continuous setting, when we have a quantitative response variable, we had all these assumptions about normality. But in the logistic regression setting, our response is a binary variable or an indicator variable, in which case we're more in line with the binomial setting. And so for the logistic regression to be valid, we assume that the binomial setting holds, and not that it just and what do we mean by holds? Because remember, we have these two populations, for instance, the low salt diet group and the high salt diet group. So, or we have the profitable movies and the unprofitable movies. So what we mean is that the binomial setting holds for each value of x. In particular, just to remind us, it's been a while since we looked at proportions and the binomial setting. We assume that there's a fixed number of observations n. Each observation falls into one of the two categories, so you can't be in both categories, it's one or the other. And then the probability, so this we usually put as a success or a failure. And the probability of success is the same for each observation. And remember, we're using P is equal to the probability of a success. And then finally, we assume that all observations are independent. Now, if we're in the case which we're about to look at, that there are multiple explanatory variables, not just one. Remember that when we have multiple explanatory variables, then if they're factors, then it has to do with each combination of those x values. And when it's not, the idea is that if we fix a set of the x's, then we can look at what's the odds of our event happening or of odds of a success and model the log odds there. So the binomial setting has to hold for each distinct value or combination of our x's. So let's look at this multiple logistic regression setting. In the population, what we're doing is modeling our log odds as being the ln of p over 1 minus p. And now what you'll see is that we're using the value q. So if there are q predictor variables. So in here, we use q predictors, or for the number of predictors, because P is already used for the probability of success. So remember, in our regression setting, linear regression setting, we always talked about there being P predictors. We don't want to talk about P predictors now because we don't want you to get confused between the number of covariates in the model and the probability of a success. So let's work through multiple logistic regression setting within the context of the movie data. And you can actually refer to example 14.11 in your textbook. So in that, remember, in the movie setting, we had several variables of interest, and some of those were and what we're going to do now is look at the response being whether the movie is profitable or not. The way we calculated that was that we said if the total US revenue was greater than the budget, the movie budget, the movie was profitable. Otherwise, it was unprofitable. And what we want to do is model that, including 3 explanatory variables, one being log opening, the other being the number of theaters that it's in, and the last one being opinions, opinions on the movies. So the population model would be that the log odds of being profitable is equal to beta naught plus beta 1 x1, where this is, so we can let log opening be our x1, theaters be the x2, and opinions be the x3. So here's our linear regression setting, and just to write this in words, this is equal to log odds of movie being predictable. Profitable. And so now it's linked with these 3 different variables through our regression line. Okay, so if we fit the data or this model in SPSS, there's a series of different tables that might come out as output. We're looking at a subset of that output. So this is page 170. And one of those is that is labeled as omnibus tests of model coefficients. So they're looking at different types of tests on our coefficients. One of this is because I believe when you fit the logistic regression, well, a multiple logistic regression, it automatically tries to do one of those forward or backward type selection methods. So the only one that we're really interested in is this last line where it says model. We can ignore these. These lines. And then we also have our standard table of coefficients where we have our variables listed. What's interesting here is that constant is put at the bottom, as we also saw in the simple logistic regression setting. We have B, which is the estimates of our model parameters or the slopes and the intercept, standard errors, the Wald statistic. Remember, this is equal to our capital X squared, which is equal to B over SE squared. And then we usually have our p-values as well. So if we're given this type of output, what does our regression line look like? Well, in the table where it says constant, that's associated with their B naught. The opinion is log opening was B1, the theaters is B2, and opinion is associated with B3. So here is what our fitted line looks like. The log odds is equal to B naught, so minus 0.404, plus B1 L opening, so that's plus 2.001. And then B2 is negative, so we get minus 0.001 theaters, and then another negative coefficient, so minus 0.214 opinion, okay? And then we can also think about an overall test on the betas, where the null hypothesis is that beta 1 equals beta 2 equals beta 3 equals 0, versus the alternative that at least one of the betas is not equal to 0. And what we can see is that we're making a test that's involving 3 different coefficients. So our X squared Wald statistic, or I should say chi-square statistic, has a value of 18.497, and the degrees of freedom is equal to 3 because we're testing in the general setting. This would be that it's beta 1 equals beta 2 up to beta Q. Okay, and this value, 18.497, we can find from up here. So this model line has associated with it H naught beta 1 equals beta 2 equals all the way to beta Q equals 0. And in the movie setting, our Q is equal to 3. We're also given the degrees of freedom here. If we want to look up we see that the p-value given on our SPSS output is 0.000. In our, if we actually had to look this up in a table, what we want to do is look up the probability that our chi-square statistic is greater than or equal to 18.4, and this should be 497. So that's such a large value, it doesn't actually matter whether that typo doesn't make a difference in our response, or in our answer. We want to look up degrees of freedom equals 3, and here is our chi-square table. Degrees of freedom is the third line here. What I can do to help us focus is cover this up to there. And what we want to look up is where do we hit 18.4? If you move this over, we can see that 18.4 is greater tun any value on our table. The smallest area we have, or the highest chi-square value, is 17.73. That's associated with area 0.0005. So all we can say is we know that the area is less than 0.0005. Okay, so that is what we have here, 0.0005. Now in SPSS, we had our significance is equal to 0.000. What that actually means is that our p-value is less than 0.001. Okay, so it is consistent. This is evidence to reject our null hypothesis. So we reject H naught and conclude that at least one slope parameter is significantly different from 0. And now that we've done this test, we know, okay, some of them are unequal to 0, but we don't know which ones. And even if we knew which ones, we don't actually have a good handle on how different they are from 0. So it's the magnitude of those differences. So that leads us to investigating which specific ones are non-zero. And what we're going to do is work through the hypothesis test and confidence intervals for each one of the slope parameters in turn. So let's first look at beta 1, which is associated with the variable log opening. If we want to look at the odds ratio, what we can do is look at our table of results, where we have that the B1 is equal to 2.001. So our odds ratio is given by e to the B1, which gives us a value of 7.396. So this is the odds ratio for movie being predictable and that's associated with increase in L opening. Okay, so if the log of the opening weekend revenue increases by 1, then the odds ratio of the movie being, so the odds of the movie being profitable is about 7.396 times the odds of the movie not being profitable. So the opening weekend, we can also see, yes, that is a large estimated difference. So the null hypothesis for testing that beta 1 is equal to 0 versus unequal to 0. We can look at the Wald statistic. Remember, that was the B over the standard error of B. So 2.001 over 6.2, and then square that ratio, we get 10.419. That's what's written as your Wald statistic value in the SPSS output. We're only testing one parameter. So our degrees of freedom is equal to 1. And then the p-value is equal to the probability that a chi-square random variable is greater than or equal to our observed value of the test statistic. So that the chi-square value is greater than 10.419. And then if we look that up in our table, chi-square table, since it's only 1 degree, we have to only look at the first row, and we're looking for the value 10.419. So the first row is for degrees of freedom equal to 1, and what we can see is that 10.4 would fall somewhere in between these two columns. So the p-value is going to be between 0.001 and 0.0025. Oh, I have this written backwards. This should be 0.001 is less than, our p-value less than 0.0025. Always make sure that our intervals make sense. Okay, so what if we say, what we can see is that for any reasonable level of alpha, this beta 1 is significantly different from 0. And remember, if beta 1 is equal to 0, let's just do this on the side. Under h naught, e to the beta 1 equals e to the 0 equals 1. Okay, so doing a test that beta 1 equals 0 is the same as doing a test that the odds ratio is equal to 1. Okay, so that should be a 0. So we see that the odds ratio from our test results, statistical test, is significantly different from 0. So let's see how different it is. In order to get the odds ratio, the 95% confidence interval for the odds ratio, we first have to build a 95% confidence interval for beta 1 itself. So that looks at our statistic for B1 plus or minus Z star times its standard error. We can pull the B1 and the standard error of B1 from our SPSS output, and we come up with an interval of 0.7858 up to 3.2162. But we're not done yet. That's just for beta 1. To get the confidence interval for our odds ratio, we need to exponentiate the endpoints. So once we do that, we get an odds ratio of 95% confidence interval for the odds ratio being 2.194 and 24.933. So what we can say is that 95% CI for OR1 does not cover 1. So result is significant at the 5% level. Okay, so what else do we want to look at? We can see, and it's no surprise, even when we did the simple linear regression, L opening was highly significant. Once we've added in these other two covariants, it is still statistically significant. And that also does make sense because part of the revenue is based on the revenue in the opening weekend. Okay, what about the second model parameter or a second slope parameter, beta 2, which is associated with theaters. Again, we can take the odds ratio being calculated as e to the b2. We get an odds ratio of 0.999. This is very close to 1. OR is just below 1. But it's slightly smaller. The question is this significant? Probably in any meaningful setting, no, but statistically, who knows? Based on our data, what we find when we do a test that beta 2 equals 0 to beta 2 unequal to 0. So this is equivalent to saying equivalent to H naught OR2 equals 1 versus HA OR2 unequal to 1. Our test statistic, we can read this right off of our SPSS output, is 3.354. This is our walled statistic. And then our p-value is calculated by the probability that a chi-square random variable with 1 degree of freedom is greater than or equal to 3.354. When we look that up in table F, we find that our p-value lies between 0.05 and 0.1. That means at the 5% level, it is greater than 0.05 or than our alpha. So our result is not significant at the 5% level. If we calculate the 95% confidence interval, we get beta 2 plus or minus, this is just for the slope parameter itself, z star times its standard error, and then we get our interval, which covers 0. When we exponentiate it, we have e to the minus 0.00296, which gives us 0.997, and then on the upper end we get 1.001. So this thing covers 0, not surprising. We did a test and it said that beta 2 is not significantly different from 0. And what we see here is that the 95% CI for the odds ratio is narrow and covers 1. So that's in line with the thinking of our test in terms of the null hypothesis being that the odds ratio is 1 versus not equal to 1. Okay, so what we showed is that our B2 indicates there's a slight decrease in profitability associated with an increase in the number of theaters where it's released, the movie's released, but that is not a statistically significant result. Finally, for beta 3, we want to look at we're thinking about the parameter, the variable opinions. What do we find here? So the odds ratio, so again, similar to what we talked about at the very beginning of the lecture, is 0.807. So what this is telling us is that the odds ratio is associated the odds of being profitable is reduced by factor of 0.807 when opinions increases by 1 unit. Okay, so we need to go back and look at exactly what that variable opinions was for us to make sense. If it has to do with the number of postings or of opinions for the movie, it might be that when a movie when more opinions are posted about a movie, they tend to be more negative ones, and so the odds of it being profitable might go down. But again, we have to go back and look at what the variable opinions actually represents to be able to interpret that well. I don't have, well, the textbook doesn't actually have chapter 14 in hard print, so it's not something for me I can look up at the moment. But if we do our test, because the question is this a statistically significant result? We'll see that a test for that beta 3 equals 0 versus unequal to 0 is associated with a Wald statistic of 0.588. This is a pretty small statistic, at least relative to the other ones we've been looking at. But again, this is on 1 degree of freedom. So we want to look at the probability that a chi-square random variable is greater than or equal to 0.588. And unlike some of the other tests that we did, I'm just going to pull up our table F. We see that the value 0.588 does not appear on this table or doesn't fall in any intervals. It's off the end point. So that means that the area to the in the upper tail of 0.588 is greater than 0.25. So that's about all we can say using our table F, that the p-value is greater than 0.25. And of course, if we had the SPSS, the full SPSS output, that would actually give us what the significance value was to 3 decimal places. And the 95% confidence interval for beta 3, we can calculate that in the usual way, and we end up getting a value of minus 0.761 up to 0.333. But that's just for beta 3 itself. What we can see is that this covers 0. If we look at our confidence interval for the odds ratio itself, we get an odds ratio that for the 95% confidence interval ranging from 0.467 up to 1.395. This one covers 1. And we can see that it's in line with this result, our estimated odds ratio not being statistically significant. Now, often in output and actually in a lot of research papers, they're not necessarily interested in the p-value because the p-values don't give you an idea of what potential values or likely values of the true odds ratio may be. So often what they like doing is just reporting the estimated odds ratio and the 95% confidence interval. So here I have the confidence interval. If we actually wanted to include our OR hat, often these would go in the opposite order, then we can do that as well. We would have for L opening, it's 7.396. For beta 2, we get it to be 0.999. And for beta 3, we have 0.807. Now, if you compare this output to your textbook, there they have some mini tab output, and there may be differences in this third decimal point, mainly because what we based all of our hand calculations on was the SPSS output, which only gives us the results up to 3 decimal places. So again, this is emphasizing that not rounding until the very, very end of our calculations in the general setting is important, because your answers may not be correct up to that 3rd decimal place. Okay, so that is all that we are going to be covering for this course. As I mentioned in the beginning, this has been a very interesting and dynamic semester. What I'd like to say is that despite all of this coronavirus interruption, and I know that it has added stress to a number of you out there, it's been an enjoyable class to go over this. As I mentioned at the beginning of the semester, I've taught the first half of this course. This was my first time going through the second half. I appreciate your patience because I know I did not have the notes and everything set up the way that you may have had them last semester. But I hope that you have, one, learned something in this course about how to do inference in these different settings. 2, I hope that you've enjoyed going through the material, and you should be proud of yourself that you've looked at this textbook and you went through from chapter 1 all the way to not just chapter 13 where this book ends, but chapter 14, which is one of the supplementary chapters. So kudos to you for that. I wish you luck in this class, in your other courses as you move forward. And, my general, usually I would say I don't want to see you in my class next year. And on one hand, I do mean that, but on the other hand, I hope that if there are some of you who are taking it next year again, I do see you, because I much rather prefer the face-to-face meetings than these virtual or online ones. So I hope that you will be in a face-to-face class in September. Good luck and have a good summer. Bye.